So we are starting a new chapter today. This is quadratic functions. So we're going to start off with a review and preview of what the chapter is going to look like. So in math, we have the search for patterns and relationships between sets of data. There's a lot of applications that will investigate the relationship between these two quantities. For example, the cost in cents per kilometer of driving a car is related to the speed at which the car is driven. So there is a sweet point at which if you keep your speed at this amount, you will burn or it'll cost you the least amount of money to drive it. And then from there you can then weigh the pros and the cons as to if I drive faster, it's costing me more money, but I am getting there in less time if that's what your choice is. The price of a watermelon is related to its weight. The heavier the mass is of the watermelon, the more money you are going to pay for it. A comparison between two sets of elements, between these sets of numbers, is called a relation. In grade 10, we looked at actually 7 different ways, there's 6 listed here, of how we could represent two quantities. So we can do that in words, that's what is right here. This is a relationship in words. We can do this as an equation, we can have a table of values, a graph, a set of ordered pairs, or function notation. Okay? These representations are going to be reviewed in this lesson. So it says, consider the following relationships between x and y. The relation is defined by the equation y equals 3x plus 5. And then the other one is the relation is defined by the equation y equals x squared plus 4. What ways are these two equations similar to each other? How are they alike?
They both have an x.
They both have an x. What else do they both have?
Y.
Both have a y.
An addition.
They have an addition. So they're alike. Both have the same variables. They are both adding a constant. They're both written in a y equals blank form. How are they different?
Different numbers.
Different numbers. How else are they different?
The x is squared on the one and then the other one is like behind the.
So one has an x squared. And then the other is x. Okay. With the x squared, what we say is we say that equation is a degree of 2 because of the squared. This one is a degree of 1 because the exponent on this x would be to the power of 1. Okay, so now what we're going to do is we're going to look at some, we're going to complete some table of values, so inputs and outputs. So I have 3x plus 5. If x equals negative 3, I would substitute that into the equation. What is 3 times negative 3?
Negative 9.
And what's negative 9 plus 5? Negative 4. If I substitute in negative 1, what is 3 times negative 1? And what's negative 3 plus 5? 2. Okay, I'm going to give you a moment. I want you to finish the next 3. Okay, so if x equals 1, I get 3 times 1 plus 5, which is 8. If x equals 3, I get 3 times 3 plus 5, which is
14.
And if x equals 5, I get
20.
20. Okay? Now we're going to do the second equation. I have different input numbers. The first one, negative 4 squared plus 4. So if I take negative 4 and I square it, I get,
Negative 16?
is it negative or positive? Be positive, because it would be negative 4 times negative 4. So 16 plus 4, 20. Okay? If I substitute negative 2 squared plus 4, what do I get?
4 is 4 is 8.
8. Okay, so finish off the next 4 again. So if x equals 0, y would equal 4. If x equals 2, y equals, if x equals 3,
13.
and if x equals 4, 20. Okay, so if you flip the page over, what I want you to do is I want you to take these two table of values and plot them on the two graphs. So these are my x values, these are my y values. So in the first graph, the first point I'd plot would be negative 3 and negative 4. So negative 3 and negative 4 would put me down here. Then the next point that was on that graph would be negative 1 and positive 2. So negative 1 moving left, positive 2 going up. So the x comes first and then the y. Okay, so again, I'm going to give you a couple of minutes. I want you to put all of those points. So this was the 3x plus 5, and this is the x squared plus 4. So what do you notice about the two graphs?
One's a line and one's a slope.
One's a line and one's not a line. One's, how would we describe that one that's not a line?
Non-linear.
Non-linear. Why non-linear, Janine?
Because it's not straight.
Because it's not straight. And that's what linear means. Okay? So in part D, it says, join the points on the graph with a straight line and extend the graph. And then for y equals x squared plus 4, join the graphs with a smooth curve and extend the graph. So with this one, what should I be using to draw my line? A ruler. Okay? So I should be using a ruler to join these points. And then I can extend the line outside the graph. With the second graph, I can't really join it with straight lines, so I can't use my ruler, but I try to draw a smooth curve. So with a smooth curve, and mine's so not smooth on that side. There we go. And so you're just putting arrows at the top to show that it extends. Okay, so I'll give you a moment to finish that up. Okay, how are these graphs the same? What do they have in common?
They both extend past the graph.
They both were extended outside the graph. What else did I do to both graphs?
Join the points.
I joined the points. So they're alike in that extend on both. We joined the points. And the reason why we joined the points is because the data is continuous. So what that means is that there can be values between the -2 and the -3 and -1. I can have multitude of inputs and outputs. The same thing with this one. I can have values between 0 and +2 on this graph. That's what makes it continuous. How are the graphs different?
One's linear and one's non-linear.
Right. So one is linear, and the other one is nonlinear. And we talked about how linear is a straight line, nonlinear means it's not a straight line. Okay, so one of the terms that was used last year when we were studying linear relations was domain and range, which, yeah, I can already see the... All domain is it's the possible values that you can input. It's the possible input values to my equation. So when you're looking at these, think of what you can't have. So things that you cannot do. You cannot square root a negative number. So if you had something that had to do with a square root, that's where you would look for a possible restriction on the domain. The other thing you can't do, you can't divide by 0. So you look to see if you're dividing by a variable. In this case here, y equals 3x plus 5, there's no square root. There is no dividing. There's no restrictions. So we can say that the domain is that x belongs to the set of real numbers. The other way that we could write this is we could say x can be any number from negative infinity to positive infinity. And then we put curved brackets. Do you guys remember from last year why curved brackets and not square brackets?
Because one means it's like continuing or something. Like you put the circle one around the infinity, right?
Mm-hmm.
Yeah.
Do you remember why?
I just remember that.
Can you count to infinity?
No.
Why not?
The highest number you think of plus 1.
It's the highest number you think of plus 1. So it doesn't actually equal this because it's not really a number per se. It's more so just kind of a concept. We use square brackets if it includes the number. Okay? The domain for y equals x squared plus 4. Again, are there x values that I can't use? Well, can I square negative numbers?
No.
Yeah. I can square negative numbers. I squared them over here. So I can square my negative numbers. I can't square root them.
Okay, yeah.
Okay? So I can pick any possible x value. So again, x is a real number. The range are my outputs, my y values. So again, if I look at this graph, the graph is sometimes a really good place to look at your domain and range as well. So if I look at this, I extend this down, my y values are just going to get smaller and smaller and smaller indefinitely. They're also going to get bigger and bigger and bigger indefinitely. So what y values make up my range? Infinity. Going up to infinity or to negative infinity. So I could say this as y can be a real number, or y can be from negative infinity to positive infinity. So now look at that other graph, that nonlinear graph. Are there y values that don't exist on this graph? So on this blue line, can you show me where I would find a y value of 0? Because where's 0? It's right here. It doesn't exist on the graph. Y equals 2 doesn't exist on the graph. Where does the graph start at? 4. And then it goes up. So on my picture it goes to 20, but can it go past 20? Yes. So we can write that in two different ways. I can say that y is going to be greater than or equal to 4. So I have to use my inequality symbols. And y is a real number. And that's where I use those curved brackets. Or I can say that y starts at 4 and goes to infinity. So the bracket is curved around the infinity, and then it's square around the 4 because 4 is part of the graph. Okay. The other thing that we talked about last year was the difference between a function and not a function. So in a function, every input only had one output. So if I look at these graphs, are these functions or not functions? There's another way that you could figure out what functions were. It was a test that we did on the graph. So what visual test can be used? That was the vertical line test. So if I draw a vertical line, or if I imagine a vertical line going through the graphs, I'm checking to see that as that vertical line passes through. So I'll show you. If I draw a vertical line, as I pass it through the graph, it only touches the graph in one spot. That's the vertical line test. So it's only going to touch the graph at one spot. Each input gives me one unique output. So these are functions. So do the graphs in part C represent function? Yes, they do. The only time that the graph really doesn't represent a function is when I have two outputs. And I have two outputs when I'm square rooting something. Because remember, when I take the square root of, let's say, 9, I can get a positive 3, or I could get a negative 3. So that would be a time where I could have two possible outputs. Okay. Linear function is a function whose graph is a straight line. We've already talked about that. The other graph, so this graph that you drew in this smooth curve, this shape is actually called a parabola. And the graphs that are parabolas are called quadratics. So quadratics have a degree of 2. That was the equation y equaled x squared plus 4. So the x value was squared. So what you're going to do in this section is we are going to graph all of these using our graphing calculators, and you're just going to sketch them. Okay? You don't have to draw x and y intercepts, you just have to sketch the graph. So on your calculator, what you're going to do is go into your y equals menu. If you have any graphs drawn in y1 or y2, you're going to clear them. And then you're going to start with your y1, 3x plus 1. Before you go to graph this, instead of pressing the graph button, what we're going to do is we're going to press the zoom button, and we're going to pick number 6. Number 6 is a standard zoom, which means it puts me back in my 10 by 10 grid, and I don't have to readjust my windows. So all you're going to do is sketch that on the page. So this line looks like this. Be careful, mine right now looks like it's going through the origin, and in the picture it's not. So I want to make sure that I draw it with some semblance of accuracy. So I'm going to give you about 10 minutes to work on these. Graph and sketch, graph and sketch, graph and sketch. Okay, so I'm going to go through now and sketch what these graphs would look like. So negative 2x squared plus 5x plus 3 is this U shape that goes upside down. Negative x cubed plus 1 is a cubic function. It has this type of a shape. X squared minus 3 is another U shape, and it goes like this. 1 over x squared, we call those rational equations because they've got a variable as a denominator. X squared plus x plus 1, that is another quadratic that looks like this. 4x is a straight line, and this one, the straight line does go through the origin. 2 to the power of x on your calculator. The power button is the one that looks like the little hat to the power of x. So this graph looks like this.
Oh, what?
No, mine was like right near the Y.
Yeah.
Yeah.
Is that like the same thing?
Yeah, I'm just exaggerating mine,
okay.
but yes, it looks like it's very, very close to the y-axis,
Yep.
and then it jumps up. Yes. Okay. Y equals negative 2/3 x minus 2 looks something like that. So it's a straight line, but this being negative, that's my slope, so it goes down instead of up. Y equals x is another straight line that goes through the origin. Y equals x squared, it's a quadratic. And then x cubed minus x squared is this cubic function that kind of makes that shape. Okay? So now what I want you to do is to go through all of the equations and write down the equations that are linear. For example, y equals x is linear. And then you're going to write down the equations of the ones that are quadratic. This, any of my u shapes are quadratic, so that's y equals x squared. And then the neithers means that it's not a straight line nor a u shape like this one. This is a neither, so that's y equals x cubed minus x squared. So I want you to write those down. I'll give you a couple of minutes to do that. What are the other equations for the linear graphs? I had y equals x. What's another one?
Y equals minus 2x squared plus 5x plus 3.
Not for a linear one.
Oh no, for quadratic.
I want the linear ones.
Y equals 3x plus 1.
Okay, y equals 3x plus 1.
Y equals 4x. Y equals negative 2 divided by 3x minus 2.
Okay. So now the quadratic ones.
Y equals minus 2x squared plus 5x plus 3.
Okay. What's another quadratic one?
X squared plus x plus 1.
Okay, so y equals x squared plus x plus 1, and there's one more.
Y equals x squared minus 2.
Yep. Okay, and then we had the graphs that were neither quadratic nor linear. Which ones were those?
Y equals minus x cubed plus 1.
Okay,
And then Y equals X squared. Are you sure that one was one? I think that's a quadratic.
y
Yeah,
equals
it's
x
in
squared.
there.
Yeah, that's
I didn't
quadratic.
see it at the beginning.
Okay, what else? There's two more.
The 1 over x.
Oh,
squared.
Y equals 1 over.
1 over x squared didn't give me that U shape that we want to see.
Y equals 2x.
Not 2x. To the power
To the
of
power
x.
of x. My bad.
Okay. So, how could you tell, given an equation, whether or not I have a quadratic or not? So what did all these have in common? Y equals x squared, y equals negative 2x squared plus 5x plus 3, y equals x squared plus x plus 1, y equals x squared minus 3.
They all have squared.
They all have an x squared. So how can you tell from the equation of a function whether it is a quadratic or not? It has an x squared. Or you could say it has a degree of 2, which is the same thing as it being an x squared. So a quadratic function is a function that can be written in the form of f of x, which just means function, equals ax squared plus bx plus c, where a, b, and c are real numbers. Okay? Or as an equation where it goes y equals ax squared plus bx plus c. The only condition is that a can't be equal to 0. Because if a was 0, what's a times x squared? Or what's 0 times x squared? 0. So this would disappear, leaving me with a bx plus c, which is not a quadratic. It has to have that x squared in it. So if we look at class example number 1, without graphing, is y equals 2x squared minus 9. Is that going to give me a U shape or a quadratic shape or not?
Yes.
Yes, because it's an x squared. What about y equals x squared minus x to the power of 5? So remember what did we write on the previous page? But what's the degree of this one? 5. This has a degree
Oh, it's the higher degree.
of 5
Gotcha.
because the higher exponent. So is this going to be a quadratic? No. So this is not a quadratic. And what about f of x equals 3 minus 2x minus 1/5 x squared? Yes. And that's because of the squared there. And it's the biggest exponent. It's the biggest number. Okay? So if you look at class example number 2, which of the following are quadratic functions? So is a quadratic function? What shape do quadratic functions give me? A U shape going this way or that way. This is not a quadratic. What about B?
Yes.
What about C?
No.
No, because it's on its side. And what about D?
No. Oh yeah.
Because it's upside down. It can be upside down.
Yeah. I just saw a line. And that was way.
Okay, so your questions are questions 1 to 5. And then 8, 9, and 10.